Hello students, welcome to EPG Pathshala. I am Dr. P.K. Ahluwalia from Physics Department, Himachal Pradesh University, Shimla. Today we are going to discuss about a module, Ensemble Theory, Classical Part 5, Canonical Ensemble, More Applications, Equipartition Theorem, Virial Theorem and Density of States under the paper Statistical Mechanics. After studying this module, you shall be able to apply the approach of canonical ensemble via partition function to two very important prototype systems in physics via partition function. And these are a collection of harmonic oscillators, classical and quantum mechanical treatment, para-magnetism, classical and quantum mechanical treatment. Compare the classical and quantum mechanical results obtained in the above two examples and see under what conditions quantum mechanical results approach classical results. We shall be able to appreciate equipartition theorem and virial theorems as classical canonical ensemble averages of the quantity xa multiplied by partial derivative of Hamiltonian with respect to xb, where xa and xb are any two of the phase space coordinates of the system. To apply equipartition theorem to derive some well-known results for systems such as monatomic gas, a diatomic gas, a harmonic oscillator and a crystalline solid. In this module, we carry forward the applications of canonical ensemble to two most important problems of the physics, a collection of harmonic oscillators and classical model of paramagnetism treated as a system of n magnetic dipoles. Also, we shall encounter relationship between the two beautiful theorems called Virial Theorem of Clausius and Equipartition Theorem of Boltzmann. These theorems have many applications to arrive at some useful results in thermodynamics and statistical mechanics. Derive Virial Theorem. Understand the importance of virial in computation of equation of state of a system and paving way for calculating pressure of the system. Calculate density of states over energy for a three-dimensional system of free particles in non-relativistic, relativistic and ultra-relativistic regime. This module has been developed for postgraduate level as per the following subtopics: canonical ensemble, more applications, a system of harmonic oscillators, classical and quantum mechanical treatment, paramagnetism, classical and quantum mechanical treatment, equipartition theorem, virial theorem, density of states over energy. Let us now examine a collection of n independent, identical linear harmonic oscillators using partition function approach as an application of canonical ensemble, which forms a precursor to the study of the statistical mechanics of a collection of photons in blackbody radiation and a collection of phonons in the theory of lattice vibrations in solids. We treat the oscillators first as classical entities and later as quantum mechanical entities to get the thermodynamics of the system and compare the results for any change in going from classical system of harmonic oscillators to quantum mechanical system of harmonic oscillators. The Hamiltonian for this set of identical linear harmonic oscillators, each having mass m and frequency omega, is given by h is equal to summation over I is equal to 1 to n pi square by 2m plus half m omega square qi square. Classical approach. Now we are ready to write a one particle partition function by recalling the definition of the partition function we studied in the earlier module. Z1 is equal to 1 upon h integral of e raised to power minus beta hi as a function of qi pi integrated over dqi dpi is equal to 1 upon h integral of e raised to power minus beta pi square by 2m dpi multiplied by integral of e raised to power minus half beta m omega square qi square dqi, or z1 is equal to 1 upon h 2m pi by beta raised to power half multiplied by 2 pi upon beta m omega square raised to power half is equal to 1 upon beta h bar omega. Here beta is equal to 1 upon kBt. The partition function for the collection of independent n linear harmonic oscillators can then be written as z is equal to z1 raised to power n, which is equal to beta h bar omega raised to power minus n. Now all thermodynamic properties can be derived. Helmholtz free energy F is equal to then minus kBt log of the partition function, which is equal to n kBt log of beta h bar omega is equal to n kBt log of h bar omega by kBt. Entropy S is equal to negative of the partial derivative of Helmholtz free energy with respect to temperature at constant n and constant v, which is equal to n kb 1 minus log of h bar omega by kBt. Internal energy E is equal to F plus Ts can be immediately obtained. That is, E is equal to n kBt. This result is in accordance with the law of equipartition of energy, according to which each quadratic term in the Hamiltonian for each harmonic oscillator contributes half kBt. Pressure P, which is nothing but the negative of the partial derivative of energy with respect to volume at constant n and constant t, is obviously equal to 0. Chemical potential mu, which is equal to partial derivative of Helmholtz free energy with respect to n at constant v and t, is equal to n kBt log of h bar omega by kBt. Specific heat at constant pressure, which is equal to specific heat at constant volume in this case, can be derived as equal to partial derivative of E with respect to t at constant n and constant v is equal to kBt. Quantum mechanical approach. Quantum mechanically, each linear harmonic oscillator is characterized by energy eigenvalue given by epsilon n is equal to n plus half h bar omega, where small n goes from 0, 1, 2, 3 up to infinity. Once again, single oscillator partition function can be written as z1 is equal to sigma n is equal to 0 to infinity e raised to power minus beta epsilon n is equal to e raised to power minus half beta h bar omega summation over n is equal to 0 to infinity e raised to power minus beta n h bar omega is equal to e raised to power minus beta h bar omega divided by 1 minus e raised to power minus beta n h bar omega, which is equal to 2 sine of hyperbolic half beta h bar omega raised to power minus 1. The partition function for the n oscillator system is then given by z is equal to z1 raised to power n, which is equal to 2 sine hyperbolic half beta h bar omega raised to power minus 1. Now we can derive all thermodynamic properties very easily. For example, Helmholtz free energy can be written as F is equal to minus kBt log of Z is equal to n kBt log of 2 sine hyperbolic 1 upon 2 beta h bar omega is equal to capital N multiplied by half h bar omega plus kBt log of 1 minus e raised to power minus beta h bar omega. Entropy S can also be written as equal to minus partial derivative of F with respect to temperature at constant n and constant v, which is equal to n times kb whole multiplied by half beta h bar omega cot hyperbolic half beta h bar omega minus log of 2 sine hyperbolic half beta h bar omega. Internal energy E is equal to F plus Ts can now be written as equal to half nh bar omega cot hyperbolic half beta h bar omega is equal to n times half h bar omega plus h bar omega divided by e raised to power beta h bar omega minus 1. This result is not in accordance with the law of equipartition of energy, according to which each quadratic term in the Hamiltonian for each harmonic oscillator contributes a term of half kBt. And here comes the difference because of quantum approach. Pressure P can then be written as P is equal to negative of the partial derivative of internal energy with respect to volume at constant n and constant t is equal to 0. Chemical potential mu, which is equal to partial derivative of F with respect to n at constant v and constant t is equal to half h bar omega plus kBt log of 1 minus e raised to power minus beta h bar omega. Specific heat can then be further written as equal to partial derivative of E with respect to temperature at constant n and constant v is equal to n kb half h omega beta whole square cosecant hyperbolic square half beta h bar omega is equal to n kb h bar omega beta whole square multiplied by e raised to power beta h bar omega divided by e raised to power beta h bar omega minus 1 ka whole square. All these results from 5 to 9 approach classical results for kBt very much greater than h bar omega. Let us now examine a collection of n independent identical spins sitting at different points using partition function approach. Each of these spins can be treated as magnetic dipoles with a magnetic moment mu. These are distinguishable as they are sitting at different locations. These form a non-interacting system in the sense that each magnetic dipole does not experience the field of the other dipoles. These magnetic dipoles can be oriented in any direction with the application of external magnetic field. Since the spins are localized, they have no kinetic energy. Para-magnetism. The Hamiltonian of such a system consists, therefore, of magnetic potential energy in the presence of magnetic field H, only which can be written as Hamiltonian is equal to minus summation over I is equal to 1 to n mu I dot H. Here, mu I is the magnetic moment of the ith magnetic dipole. We look at the system both classically and quantum mechanically and try to get some well-known result such as Curie law for paramagnetic systems. A classical treatment. In this case, equation 20 can be written explicitly in terms of orientation theta I of each magnetic dipole as Hamiltonian is equal to minus summation over I is equal to 1 to n mu I h cos of theta I is equal to minus n mu h summation over theta cos of theta. Now the single particle part function can be written remembering that three-dimensional orientation is decided by theta and phi, so that single dipole partition function can be written as z1 is equal to summation over theta e raised to power beta mu h cos of theta is equal to integral from 0 to 2 pi integral from 0 to pi e raised to power beta mu h cos of theta sine of theta d theta d phi. Putting x is equal to cos of theta, we solve equation 22 to get z1 is equal to integral from 0 to 2 pi minus 1 to plus 1 e raised to power beta mu h x dx d phi is equal to 4 pi sine hyperbolic beta mu h divided by beta mu h. So the partition function of the system can be written as z is equal to z1 raised to power n is equal to 4 pi sine hyperbolic beta mu h divided by beta mu h whole raised to power n. Now we can calculate the thermodynamic properties using the results derived in module 13. Helmholtz free energy F. F is equal to minus n kBt log of 4 pi sine hyperbolic beta mu h divided by beta mu h. Magnetization M of the system can be written as equal to minus partial derivative of Helmholtz free energy F with respect to h at constant temperature and constant number of particles is equal to n kBt multiplied by partial derivative of log of sine hyperbolic beta mu h minus log of beta mu h with respect to h. M is equal to n mu curly bracket cot hyperbolic beta mu h minus 1 upon beta mu h curly bracket closed is equal to n mu L, a function of beta mu h, where L, which is a function of x, is equal to cot hyperbolic x minus 1 upon x is the Langevin function. Here x is equal to beta mu h is a parameter giving the ratio of magnetic potential energy mu h to the thermal energy kBt. The mean magnetization in the direction of the magnetic field is equal to m upon n is equal to mu multiplied by cot hyperbolic beta mu h minus 1 upon beta mu h is equal to n mu L beta mu h. This function is drawn in the figure 1. There are two limiting cases which provide us interesting results. Low temperature or high magnetic field limit, that is, mu h is very much greater than kBt. In this limit, Langevin function saturates to 1, as is obvious in figure 1, that is, all magnetic dipoles align in the direction of the magnetic field and the net magnetization shall be m is equal to n mu. Second limit, high temperature or low magnetic field limit, that is, mu h is very much less than kBt. In this limit, cot hyperbolic x can be expanded as 1 upon x plus x upon 3 minus x cube upon 45 plus so on, and the Langevin function Lx is approximately equal to x upon 3. Therefore, m is equal to n times mu square h upon kBt. In this limit, susceptibility chi is equal to partial derivative of m with respect to h, which becomes equal to n mu square upon kBt is equal to a constant divided by temperature. This is the famous Curie law of paramagnetism, which was experimentally verified to be true for copper potassium sulfate hexahydrate. A quantum mechanical treatment. To treat the problem of paramagnetism quantum mechanically, we must note that magnetic moment of the particle involved of the system depends on its angular momentum j. Magnetic moment mu and its components in the direction of magnetic field doesn't have arbitrary values but are discrete. If angular momentum of the system is j, its magnetic moment mu is given by mu is equal to mu b, that is Bohr magneton, multiplied by g multiplied by j, where mu b is equal to E h bar upon 2 mu mc and is Bohr magneton, and g is Landau factor given by g is equal to 3 by 2 plus s into s plus 1 minus l into l plus 1 divided by 2j into j plus 1. If the particles involved are electrons, that is s is equal to 1 upon 2 with l is equal to 0, the total angular momentum j is equal to half and Landau factor g is equal to 2. On the other hand, if s is equal to 0, then g is solely due to L and g is equal to 1. Now if we take magnetic field in the direction of z-axis, the component of mu in this direction, mu z, is given by mu z is equal to Landau factor multiplied by Bohr magneton multiplied by m, where m takes values from minus j to plus j in the step of 1. Now we are in a position to write down the single partition function in the presence of magnetic field. That is, Z1 is equal to summation over m is equal to minus j to m is equal to plus j e raised to power g mu b m h beta. The sum in equation 17 is a geometrical progression with 2j plus 1 terms, with first term e raised to power minus g mu b j h beta and common ratio e raised to power g mu b h beta. Therefore, Z1 is given by e raised to power minus g mu b j h beta multiplied by 1 minus e raised to power g mu b h beta 2j plus 1 whole divided by 1 minus e raised to power g mu b h beta. This can be further simplified to give Z1 is equal to e raised to power minus g mu b h beta j plus half minus e raised to power g mu b h beta j plus half divided by e raised to power g mu b h beta divided by 2 minus e raised to power minus g mu b h beta by 2, which is equal to sine hyperbolic g mu b h j beta into 1 plus 1 upon 2j divided by sine hyperbolic g mu b h j beta divided by 2j. Putting g mu b h j beta is equal to x, equation 36 becomes Z1 is equal to sine hyperbolic x multiplied by 1 plus 1 upon 2j divided by sine hyperbolic x upon 2j. So the total partition function of the system is given by z is equal to sine hyperbolic x into 1 plus 1 upon 2j divided by sine hyperbolic x upon 2j and whole raised to power n. Now we will be in a position to calculate thermodynamic properties of the system. Let us calculate first Helmholtz free energy F. F is equal to minus nkbt multiplied by log of sine hyperbolic g mu b h j beta multiplied by 1 plus 1 upon 2j minus log of sine hyperbolic g mu b h j beta divided by 2j. Magnetization M is equal to n g mu b j multiplied by 1 plus 1 upon 2j multiplied by cot hyperbolic of g mu b h j beta multiplied by 1 plus 1 upon 2j minus 1 upon 2j cot hyperbolic of g mu b h j beta divided by 2j, or M is equal to n g mu b j multiplied by b j g mu b h j beta, where b j g mu b h j beta is Brillouin function of order j, where j is the relevant number. The plot of the Brillouin function is given in figure 2 below. From figure 2, it is clear that for large values of g mu b h j beta very much greater than 1, that is, for strong field and low temperature, the Brillouin function approaches 1 for all values of j, showing state of magnetic saturation. However, for g mu b h j beta very much less than 1, that is weak field and high temperature, the Brillouin function, knowing that cot hyperbolic x is approximately equal to 1 upon x plus x upon 3 for x very much less than 1, so that Brillouin function can be written as bjx is approximately equal to 1 plus 1 upon 2j multiplied by 1 upon g mu b h j beta multiplied by 1 plus 1 upon 2j plus g mu b h j beta multiplied by 1 plus 1 upon 2j divided by 3 minus 1 upon 2j multiplied by 1 upon g mu b h j beta divided by 2j plus g mu b h j beta 1 upon 2j divided by 3, or bjx is approximately equal to g mu b h j beta divided by 3 whole multiplied by 1 plus 1 upon 2j whole square minus 1 upon 2j whole square, which simplifies to g mu b h j beta divided by 3 multiplied by 1 plus 1 upon j. Therefore, m is equal to n g mu b whole square j into j plus 1 divided by 3k bt whole multiplied by h. And susceptibility chi can be written as equal to partial derivative of m with respect to h, which is equal to n g mu b whole square j into j plus 1 divided by 3k bt, which is once again equal to a constant divided by t, where now the constant c is equal to n multiplied by g mu b whole square into j plus 1 divided by 3kb, which is equal to n mu square divided by 3kb, with mu square is equal to g mu b whole square j into j plus 1, a departure from the classical result. In the limit j approaching infinity, Brillouin function reduces to Langevin function, that is 1 plus 1 upon 2j multiplied by cot hyperbolic of x multiplied by 1 plus 1 upon 2j minus 1 upon 2j cot hyperbolic of x upon 2j approaching cot hyperbolic x minus 1 upon 2j into 2j divided by x, which is equal to cot hyperbolic x minus 1 upon x. This is expected. J approaches infinity amounts to saying that there are tremendously large orientations in which the magnetic dipoles can align. This situation is the same as in the classical case and should yield the classical result. Let us now look at equipartition theorem. Equipartition theorem, also known as law of equipartition of energy, is a classical theorem. According to it, in classical limiting case, every canonical variable, that is generalized position and momentum, entering quadratically or harmonically in a Hamiltonian function, that is in energy, has a mean thermal energy half kBT. For example, Hamiltonian function in 3 dimensions may be written as equal to p square by 2m plus half m omega square r square plus half L square upon I plus E square plus B square divided by 8 pi. This Hamiltonian represents energy possessed by a molecule which is respectively made up of translational kinetic energy, harmonic potential energy, rotational kinetic energy, and electromagnetic energy in an electromagnetic field. Each term is quadratic in one of the canonical variables. Therefore, according to law of equipartition of energy in 3 dimensions, thermal energy E is given by 3 kBT by 2 plus 3 kBT by 2 plus kBT plus 2 kBT. Here, we have 3 canonical variables for translational motion, 3 for vibrational motion, 2 for rotational motion, and 2 each for electrical energy and magnetic energy. Proof of equipartition theorem. Suppose we have a classical system of n particles with 6n generalized coordinates qi, pi, where I goes from 1 to 3n, giving a total of 6n coordinates. We are interested in calculating the mean value of the quantity xi partial derivative of Hamiltonian with respect to xj, where xi and xj are any of the 6n coordinates. In canonical ensemble, it is given by mean value of xi partial derivative of Hamiltonian with respect to xj is equal to integral of e raised to power minus beta hqp multiplied by xi partial derivative of h with respect to xj integrated over d omega divided by integration of e raised to power minus beta hqp d omega, where d omega is equal to d3nq into d3np. Out of d omega, let us pick up integration over xj in the numerator and do this integration by parts. First, we know that e raised to power minus beta hqp multiplied by xi delta h upon delta xj is equal to minus 1 upon beta xi partial derivative of e raised to power minus beta hqp with respect to xj. So equation 48 can be written as mean value of xi partial derivative of h upon delta xj is equal to minus 1 upon beta integral of xi multiplied by partial derivative of e raised to power minus beta hqp with respect to xj dxj multiplied by d omega over the remaining coordinates divided by e raised to power minus beta hqp over omega. So integral over xj becomes integral of xi multiplied by partial derivative of e raised to power minus beta hqp divided by partial derivative of xj into dxj is equal to xi e raised to power minus beta hqp from xj1 to xj2 minus integral of delta xi with respect to xj e raised to power minus beta hqp with respect to xj. To take limits over the first term, we note that there are two possibilities. If xj are momentum coordinates, the kinetic energy tends to infinity at extremely large values, making Hamiltonian infinite and e raised to power minus beta hqp approaching 0. If xj happens to be position coordinate, the limits mean on the walls of the container in which the system is enclosed, where the potential energy is infinite, and once again Hamiltonian becomes infinite, leading to e raised to power minus beta hqp approaching 0. Thus, we can conclude that first term vanishes. So equation 50 becomes integral of xi multiplied by partial derivative of e raised to power minus beta hqp with respect to xj over xj is equal to minus integral of delta xi with respect to xj e raised to power minus beta hqp dxj is equal to minus of integral over delta ij e raised to power minus beta hqp dxj. Hence, equation 49 can be written as mean value of xi multiplied by partial derivative of h with respect to xj is equal to 1 upon beta integral of delta ij e raised to power minus beta hqp dxj d omega over remaining coordinates divided by integral of e raised to power minus beta hqp d omega, which is equal to delta ij multiplied by integral of e raised to power minus beta hqp over the whole phase space divided by e raised to power minus beta hqp over the whole phase space, which is equal to delta ij upon beta, which is equal to delta ij kbt. This is an extremely general result and is independent of the precise form of the Hamiltonian hqp. From equation 52, the following results follow immediately. If xi is equal to xj is equal to pi, then mean value of pi multiplied by partial derivative of h with respect to pi is equal to kbt, and therefore summation over I is equal to 1 to 3n over mean value of pi partial derivative of h with respect to pi is equal to 3n kbt. If xi is equal to xj is equal to qi, the mean value of qi multiplied by partial derivative of h with respect to qi is equal to kbt, and therefore summation over mean value of qi multiplied by partial derivative of h with respect to qi is equal to 3n kbt. You must be wondering, what about the statement of the law of equipartition of energy made earlier, that every canonical variable, that is generalized position and momentum, entering quadratically or harmonically in a Hamiltonian function or energy has a mean thermal energy kbt divided by 2. This can be checked easily. Let us take a Hamiltonian which is a quadratic function of coordinates. By suitable canonical transformation, it can be converted into a form h is equal to summation over j aj pj whole square plus summation over j bj qj square, where qj and pj are canonically conjugate transformed coordinates and aj and bj are suitable constants. Then it immediately follows that summation over j pj delta h upon delta pj plus qj multiplied by partial derivative of h with respect to qj is equal to 2h. Therefore, from the table it follows that mean value of h is equal to half multiplied by summation over j over mean value of pj delta h upon delta pj plus mean value of qj delta h upon delta qj is equal to half 6n kbt, which is equal to half f kbt. Here 6n are the number of degrees of freedom corresponding to number of non-zero coefficients in the transformed Hamiltonian. One can immediately conclude that corresponding to each quadratic term in the Hamiltonian, there is a contribution of half kbt, proving the statement, providing an alternative proof for the equipartition theorem. Applications of equipartition theorem. Let us take the case of a monoatomic gas. Single atom in a monoatomic gas has only translational kinetic energy, so that total Hamiltonian of the 1 mole monoatomic system can be written as summation over I is equal to 1 to n pi x square divided by 2m plus pi y square divided by 2m plus pi z square divided by 2m, where n is Avogadro's number, so that there are 3n quadratic terms in the momentum coordinate in it. According to law of equipartition of energy, the energy of this n particle monatomic gas can be written as E is equal to 3n kBt divided by 2 plus 3 by 2 RT. The molar specific heat at constant volume Cv is therefore equal to 3 by 2 R. Using Cp minus Cv is equal to R, specific heat at constant pressure is then given by Cp is equal to 5 by 2 R. The ratio of the two specific heats, gamma, that is equal to Cp upon Cv, becomes equal to 5 upon 3, a well-known result. A diatomic gas. Each particle of the gas in this case is made up of diatomic molecule, which can be assumed to be a dumbbell-shaped rigid rotator with a rotational symmetry about the line joining the nuclei of the two atoms along z-axis. So, the Hamiltonian of the diatomic molecule has three translational kinetic energy terms, quadratic in three components of the linear momentum, and two terms corresponding to rotational kinetic energy, quadratic in two components of J, which can be written as sigma I is equal to 1 to n over pix square over 2m plus piy square over 2m plus piz square over 2m plus jix square upon 2i plus jiy square upon 2i, where j is angular momentum and I moment of inertia. Hamiltonian thus has 5n quadratic terms. According to law of equipartition of energy, the energy of this n diatomic molecule system can be written as E is equal to 5 upon 2 n kBt is equal to 5 upon 2 RT, where n is Avogadro's number. The molar specific heat at constant volume therefore is Cv is equal to 5 upon 2 R. Using Cp minus Cv is equal to R, specific heat at constant pressure is then given by Cp is equal to 7 upon 2 R. The ratio of the two specific heats, gamma is equal to Cp upon Cv, then becomes equal to 7 upon 5, a well-known result which agree very nicely with experimental results at room temperature. It must be mentioned here that if we relax the condition of rigid molecule in this discussion, we expect molecule to vibrate as a one-dimensional harmonic oscillator having energy which is partly kinetic and partly vibrational, contributing two additional terms so that each molecule contributes vibrational kinetic energy of 2 into half kBt, so that E is equal to 5 upon 2 n kBt plus n kBt is equal to 7 upon 2 RT, so that specific heat at constant volume is equal to 7 upon 2R, and specific heat at constant pressure then becomes equal to 9 upon 2R, and the ratio of specific heats becomes equal to 9 upon 7. The observed values do not agree with experiments, indicating that at room temperature, diatomic molecule has no vibrational motion. The vibrations get excited only in the case of high temperature limit. Now let us take the case of a crystalline solid. A simple model of crystalline solid consists of a collection of atoms, with each lattice having one atom, where it cannot move or rotate but can behave as an independent harmonic oscillator. Each oscillator having 6 quadratic terms, 3 for kinetic energy and 3 for potential energy. That is, PIX square divided by 2m plus PIY square divided by 2m plus PIZ square divided by 2m plus half K QIX square plus QIY square plus QIZ square. So, according to law of equipartition of energy, we have energy of 1 mole of a solid given by E is equal to 6n multiplied by half kBt is equal to 3RT. Thus, molar specific heat of a solid at constant volume Cv is equal to 3R, well known Dulong and Petit's law. This is found to be the case at high temperature, but is not true at low temperatures, and we need to go beyond classical law of equipartition of energy and quantum mechanics invoked as was done by Einstein. Virial Theorem. In classical mechanics, the product Pi multiplied by partial derivative of h with respect to Pi, which is equal to Pi Qi dot, and Qi multiplied by partial derivative of h with respect to Qi is equal to minus Qi Pi dot have a special significance. The second expression, which is a product of position, coordinate and generalized force, is called virial, and when summed over all I, it means value gives virial theorem of statistical mechanics. That is, virial is equal to mean value of summation over I is equal to 1 to 3n Qi Pi dot, which is equal to negative of mean value of summation over I is equal to 1 to 3n Qi partial derivative of h with respect to Qi, which is equal to minus 3n kBt. Virial has a very interesting relationship with the physical quantities of a system, and starting from it, equation of state can be derived. Let us take the case of an ideal gas. It is enclosed in a container, and walls provide the only external force to keep the gas confined in the form of external pressure P. So here we have a force which is equal to minus pressure multiplied by the elemental surface area ds acting on an area element ds of the wall. The virial of the ideal gas can be calculated as VID is equal to summation over I is equal to 3n Qi Pi dot is equal to summation over I is equal to 1 to 3n Qi Fi, which is equal to minus P integrated over whole of the surface R dot ds, where R is the position vector corresponding to the surface element with a particle in its vicinity. Using divergence theorem, we have virial of an ideal gas equal to minus P integrated over whole of the volume, divergence of R equal to minus 3 PV. Applying virial theorem, we have ideal equation of state PV is equal to nKT. Furthermore, kinetic energy of an ideal gas, say Ek is equal to 3 by 2 nKBT is equal to minus virial of the ideal gas divided by 2. Therefore, virial of the ideal gas is equal to minus 2 times Ek. Please note that virial has many interesting applications where it can, from the knowledge of two-particle potential, be used to calculate the equation of state of the system, which becomes very useful in calculation of pressure computationally. We have till this point focused on the number of microstates in a region of phase space and arrived at a result that for a system with f degrees of freedom, a volume 2 pi h bar raised to power f in the phase space contains 1 microstate. However, in many practical situations, for example, in condensed matter physics, we are interested in finding the number of states which are available to it in a small energy interval epsilon and epsilon plus d epsilon, the so-called density of states. This important number can be obtained if we know relationship between energy epsilon and momentum p, also called dispersion relation. Density of state over energy. Dispersion relations for a free particle system for non-relativistic, ultra-relativistic, mass-neglected or massless particles and relativistic particles are given in the table below. For non-relativistic, dispersion relation is epsilon is equal to p square upon 2m. For relativistic, epsilon square is equal to c square p square plus m square c power 4. And for ultra-relativistic, the dispersion relation is epsilon is equal to cp. Let us derive for a three-dimensional system the density of states, curly d epsilon, the number of states of a particle per unit volume per unit energy range about epsilon. Let us begin by counting the number of states for a free particle in 3 dimensions in small region of phase space dq bar dqp. Then, since particle has 3 degrees of freedom, we have number of states in phase space volume dq bar dqp is equal to dq bar dqp divided by 2 pi h bar whole cube. If the particles have some internal degrees of freedom, let us denote this by g, then the above relation becomes number of states in phase space volume dq bar dqp is equal to g multiplied by dq bar dqp divided by 2 pi h bar whole cube. Let us assume that system is homogeneous. Then this number is independent of the position of the phase space volume element. Then we can integrate over the position coordinates to obtain number of states in momentum space volume dqp is equal to g times v dqp divided by 2 pi h bar whole cube. Now if we take system to be isotropic, this number depends only on the magnitude of momentum p. We can then integrate over angular variables theta and phi so that we get number of states between p and p plus dp is equal to g times 4 pi v p square dp divided by 2 pi h bar whole cube. Now let the density of state over energy be the number of states of a particle per unit volume per unit energy range about epsilon. Then V multiplied by the density of state multiplied by d epsilon is equal to g times 4 pi v p square dp divided by 2 pi h bar whole cube, or d epsilon is equal to g times 4 pi p square upon 2 pi h bar whole cube multiplied by dp upon d epsilon. Now by using dispersion relations discussed earlier, we can get density of states for each of the cases for a 3-dimensional system as given in table 2 below. That is, for a non-relativistic system, the density of state is given by g upon 4 pi square 2m by h bar square raised to power 3 by 2 multiplied by epsilon raised to power half. For a relativistic system, it becomes g upon 2 pi square epsilon into epsilon square minus m square c power 4 raised to power 1 by 2 divided by c h bar whole cube. And for ultra-relativistic case, the density of state becomes g upon 2 pi square epsilon square divided by h bar c whole cube. So students, let us summarize what we have learnt in this module. In this module, we have learnt how the thermodynamic properties of a given n-particle system can be obtained from the knowledge of the partition function of the system. We first saw a system of harmonic oscillators described by the Hamiltonian h is equal to summation over I is equal to 1 to n pi square by 2m plus half m omega square qi square. We studied various physical quantities associated with it in classical approach and quantum approach. For example, partition function, Helmholtz free energy, entropy, pressure, internal energy, chemical potential, specific heat. I hope you must have noted the difference between classical results and the quantum mechanical result in the case of the collection of n harmonic oscillators. Then we studied paramagnetism both classically and quantum mechanically. The Hamiltonian for a classical system of magnetic dipoles in a magnetic field was written as H is equal to minus summation over I is equal to 1 to n mu I dot H is equal to minus summation over I is equal to 1 to n mu I H cos of theta I is equal to minus n mu H summation over theta cos of theta. And we studied very interesting physical quantities associated with it both classically and quantum mechanically. These included magnetization in high magnetic field or low temperature limit, magnetization in high temperature and the low magnetic field limit, susceptibility in high temperature and the low magnetic field limit. You must have seen the difference between the classical approach and quantum mechanical approach. That law of equipartition theorem states that every canonical variable, generalized position and momentum, entering quadratically or harmonically in a Hamiltonian function, that is energy, has a mean thermal energy kBT by 2. We also learned how to derive law of equipartition of energy in its most general form, that is ensemble average of xi partial derivative of h with respect to xi j, which is equal to delta ij kBT, where xi and xj are any of the 6 n coordinates. We also learned how to apply law of equipartition of energy to get in the classical limit internal energy E, molar specific heat at constant volume, molar specific heat at constant pressure, and the ratio of the specific heats gamma for a monatomic gas, for a diatomic gas with and without vibration, and a crystalline solid, highlighting the limitations of the approach. How to calculate virial of the ideal gas was also learned. Virial of an ideal gas is equal to summation over I is equal to 1 to 3n QIPI dot the ensemble average, which is equal to minus ensemble average of summation over I is equal to 1 to 3n QI delta H by delta QI is equal to minus 3n kBT, and how it can be used to get equation of state of the ideal gas. We also learned how to calculate density of state over energy of a three-dimensional gas of free particles. The density of state over energy d epsilon was written equal to the degeneracy g multiplied by 4 pi p square upon 2 pi h bar whole cube multiplied by dp upon d epsilon for non-relativistic, relativistic and ultra-relativistic, that is massless gas, and is given by, for non-relativistic case, g upon 4 pi square multiplied by 2m on h bar square raised to power 3 by 2 epsilon raised to power half. For relativistic, g upon 2 pi square epsilon into epsilon square minus m square c power 4 raised to power half divided by c h bar cube. And for ultra-relativistic case, g upon 2 pi square epsilon square upon h bar c whole cube. Thank you.